friends, so welcome to day 24 for solving problem of the day from GFG. So let's look at today's problem. Okay, so here is our problem. Given two integers a and b, the task is to find an integer x such that x XOR a is minimum possible and the count of set bits in x is equal to the count of set bits in b. Okay, so let's understand the question. And before starting the question, actually, I want to share something. So this is our example. Now forget about this. There is something to know. Okay. First thing is an algorithm called Kernighan's algorithm. Okay. So this is an algorithm which actually do what? That suppose I have a number like this. Okay. So what it will do? It will tell me the number of set bits. So what the word set bit means? So set bit means that in a binary number, the number of ones or the bits. These are bits, right? 0 and 1 are bits. So bit which is on means 1 and off means 0. So set bit means 1. So count of set bits, count of 1, it gives count of set bits. Okay, so which is 3 actually for this case. And the magic here is it will not go from here to here, then here, then here, then here, then here, or you can say from here, then here, 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 here. It will not go like this. That is the magic in this algorithm actually. Okay, so how it will go is it will go directly to this, then it will go directly to this, then it will go directly to this. So that's the magic actually. Okay, so I am not describing the Kernighan's algorithm here, as it is fully explained in any videos in YouTube. So let's take an example for Kernighan's algorithm. Okay, let's just take an example. So suppose this number. Now what I will do according to the algorithm is, suppose this is my n, so I will calculate 2's complement of n. Okay, 2's complement of n. So how to compute 2's complement? So actually this is a short trick, that minus n is actually the 2's complement of n. Okay, so what is actually a 2's complement? So suppose I have a number 101, binary number. So what I have to do? I have to just change its bits. So here is 1, I will put 0. Here is 0, I will put 1. Here is 1, I will put 0. So just what can I say? Just change the bits to its opposite. Okay, so this is actually 1's complement of this number. Okay, now if I add 1 to my answer, it will become 0, 1, 1. Now this is my 2's complement, okay, of the same. Okay, so that's the thing actually. So I have a number, I will change its bits to its opposite bits, and I will add plus 1. Okay, so that's 2's complement. So for Kernighan's algorithm, what I will do is I will compute 2's complement of it. So the 1's complement first compute the ones complement, it will be like 0 1 0 0 0 1 0 1 0. Now see that if I add plus 1 to it, it will be like 0 1 0 0 0 1 0 1 1. Now if I, so this is 2's complement, okay, after adding plus 1 to it, after adding 1 to it. Now if I add these two numbers, which one, this one and this one, so what will happen? Look very carefully. Actually after doing 2's complement, almost every places will contain 0 for 2's complement, either 0 for 2's complement or 1 and 1 for n, or 1 for 2's complement and 0 for n. What I mean is, take any position, this position, here is 1, right? So obviously my 2's complement will be 0, okay, and only there is one place where my position will give 1 simultaneously. So at this position both of them are 1. For all of the rest positions, this is 0, this is 1, this is 1, this is 0, this is 0, this is 1, this is 1, this is 0. So why it happens? Because we first flip the bits, right, in case of 1's complement, then we add 1 to it. So suppose the last bits are like this, suppose this is the case, then the 2's complement will be like this, right? So after adding 1, let's do like this, okay, let's take this example, 1 0 0 0 1. So its 1 complement is what, 0 0 1 1 1, right? So if I add 1 to it, it will be like 0 1 0 0 0. Now look at it, this is what, this is the yeah, this is the 2's complement, right? And what I have said, that in most of the places, if there is 1, here is 0, here is 1, here is 0, here is 0, here is 1, here is 1, here is 0, here is 1, here is 0, here is 1, here is 0, 0 1 1 0 0 1. Only here is my 1 and 1, right? So the place where both of them will give me as 1 will be my first set bit in my n. Look at here, this position is actually giving me simultaneously 1, so this position is actually the first position of a set bit, starting from left to right to left. So that's why I got this, right? So it's actually my right, it giving me actually rightmost set bit, okay. So in this case you may say that here is a 0, here is a 0, here is 0 0 0 0 and 1 1 and 1, then up again 1 0. So actually the thing is that before just that position where I get simultaneously 1, before that position all will be like 1 0 or 0 1, 1 0 or 0 1, like this, okay. And after that, either this is the end of my binary number, and if there are any other numbers, all will be 0, and here also all will be 0, because this must be the last set bit, because what I have said, that the position where I will get both as 1 will be my first set bit. So for 1 1 0 0 0, this position is actually the first set bit, right? So if there is any other number, it will always be 0, and here also it will always be 0, okay. So actually they are giving me 0. So if I AND these two, I will get 0 1 0 0 0. So I get the position, I get 1 at that position where my first bit was set, right? So that's the thing actually. If you don't understand, nothing to worry, just see on the YouTube, it's very well explained, I can say, okay. So there is actually 2 cases, okay. So I am just clearly saying there is only 2 cases. This case 1 0 1 0 0 and suppose this case 0 1 0 1 1. In this case, if I do 1's complement, it will be like 0 1 0 1 1, and for this case it will be like 1 0 1 0 0. Now I add 1, so it will be like 0, it will be like 0 1 1 0 0, it will be like 1 0 1 0 1. Now for this number, this is the position for first set bit starting from right to left. For this number, this is the first position of set bit. This is my n, okay, this is my minus n. So if I add both of these, see the first position after all are 0, okay. So if I add this, there is 1, there is 0, there is 0, there is 1. So if I add this, it will become 0 0. Here is my 1 and all other are zeros. Here also it will be like 0 0 and these two, okay, and these two 0 0 1. So at this position actually my bit was set, right? At this position my bit is set, right? So that is why it's giving me this. Now what after that? It is just giving me the rightmost set bit. After that I will do that m equal to n minus this number. Suppose this rightmost set bit, I will just do this, and my number will become what? In this case my number will become, so 1 0 1 0 0 minus 0 0 1 0 0, it will become 1 0 0 0 0. Now again I will do this thing. This is my n now, and I will calculate minus n. It will be like 0 1 1 1 1 plus 1, which is 1 0 0 0 0. Okay, in my n this position was set, in my this rightmost set bit this position is set. So again minus this from this, 1 0 0 0 0 1 0 0 0 0, so I will get 0. So I'll do the thing until I get this 0, and I will just count plus plus, and I will get just 2 set bits for this case. Okay, so that's the thing actually. Okay, so this is Carnot-Li's algorithm. This is the first thing you should know. The second thing is the example. Okay, so now let's look at the example. So what's the question is saying, that I have given two numbers, a equal to 3, b equal to 5. Now what happens is I have to find the number x such that the number of set bits in x should be equal to the number of set bits of this b, okay, which is 5. So 5 is written as 111, I think, 101, sorry, 101. So the number of set bits is 2, right? So here also in my x, the number of set bits should be 2, and also among all those numbers where the number of set bits is 2, among all those numbers where my number of set bits is 2, like 0 1 1 1 0 1 1 1 1 1 1 0 1 1 1 0 1 1 1 0 0 1 1 0 1 0 1 0, like all these 1 0 0 0 0 0 1 0 0 1 0, all like this. If I do XOR sign is this. There are many results, like if I do XOR with this and a, I will get an result. If I do XOR with this and a, I will get another result. Do this and a, get another result. So among all of them, which one, this one or this one or this one or this one, which one is giving me the minimum result, minimum number, that I have to find. Okay, so for this case, our example, see, in our example, so a is actually what, 0 1 1, b is 1 0 1, so x is given as 3, my answer. So why it is so? To say that a XOR x is actually what, 1 0 1 1 XOR 0 1 1, which is 0 1 1, that is 3. And also the number of set bits in my x is 2, which is same as the number of set bits in b. First clear the question. Okay, here is my a, b given. I have to find x, where x actually specifies two conditions. One, that the number of set bit of x should be the number of set bit of b, and the second number is it should give the minimum result when doing XOR with a. Okay, so XOR a should be minimum of all possible x's. So there are many answer possible, right, which is just containing number of set bit as number of set bit of b. So among all the results, there is the x which actually after doing XOR with a will give me a minimum number. That is my result actually. Okay. So in this case, it is actually like this. So how the result is coming? So I cannot do like 0 1 1 1 0 1 1 0 0 1 1 0 1 0 0 1 1 0 0. I cannot do like just list all those numbers and do XOR and find which is minimum. I cannot do like this, right? There must be some process. So let's look at the process. Okay, erase this. Look at the process. Okay. So first thing, what does XOR do? Suppose I have 1 and 0 and I do XOR. What will be the result? So remember one thing, that in XOR 1 is powerful very. So 1 is very powerful. Okay, 1 is very powerful. Why? If you do XOR with anything, if there is 1 present here, if you do XOR with a number by 1, okay, so if you do XOR with a number by 1, it will just give the opposite bit, which is 1. 0's opposite is 1, it will give me 1. If you do XOR with 1, here is 1, it will give you 0. 0 is powerless. Here is 0, it will give it as it is. Okay, here is 0, here is 0, right? It will give as it is. Okay, 1 is very powerful. It will flip the bit and give you the opposite bit. Okay, so if I give you two numbers 0 1 1 and 0 1 1, so if I XOR these two numbers, so what will be the result? So 1 and 1, right? So 1 is present in any of them, so what it will give? 0. Here is also 1 1, gives 0. Here is 0 0, gives 0, right? Okay, so one thing I should say, so 0 1 1 XOR 0 1 1 is not 0 1 1, it's 0 0 0, sorry, which is 0. Okay, whatever. Now yeah, so 0 1 1 and 0 1 1, it will give me answer 0 0 0. Now 0 1 1 and 1 0 1, what will be the answer? Here is 1, here is 1. So 1 is very powerful, it will give an answer 1 in case of 0 and 0 in case of 1. 0 is powerless, it will give like this. So 1 1 is 0, 1 0 is 1 0 is 1, 1 0 is 1. So which of them are bigger? In our example it was A, right? It was A, and the given answer was X, right? It's another X, suppose X dash. So it's giving 0 here, it's giving 6 here. Okay, so which is minimum? This is minimum, so our answer is right, because 0 is less than 6. Now why it's giving a bigger number? Why? Can you see one thing? There is one thing to notice here, which is that if two bits are 1, it will give you 0. right? If two bits are opposite like this, it will give you 1. See, 0 and 1. If you XOR 0 and 1, uh, 0 and 1, or you can say like this, it will give you 1. So to find the minimum number, I have to find, I have given this number, right? So I have given this number. I have to find this number, which is colored in red. So I have to find an answer which will give me maximum zeros, right? Not ones, right? Which will give me a maximum 0 will be my answer. In this case, this x is actually giving me zeros, right? In this answer 101, it is giving me 1. Why it is giving me 1? Because in the position of this a where there is a 1, it's actually having a 0. If a is having a 0, it's actually having 1. So in case of opposites 1 and 0, so if you XOR 1 and 0, it will give you 1, or if you XOR 0 and 1, it will give you 1. So that's the thing, actually that's the tricky part. You cannot have an opposite bit in the position of same position of a, right? So what I want to see is, here is my 0 1 1, here is my 1, here is my also 1. So what our target is, it should have 1 here, because then it will give 0. It should have 1 here and it will give 0. Can it be given as 1? No. Then will opposite give a 1 here. So I don't want here, I want a 0 here. So what I will do, I will just keep 0 here, okay? Because 0 0 is 0. Now that doesn't matter actually. In case of 0, here is a 0, that doesn't matter. If here is a 1, I will give here 1, right? So I have to find that in my a, where is the 1s? So definitely my answer will contain 1 in that places, right? Because other than that, nothing is possible. Suppose this is my b, which is 1 1 1, and this is my a 1 0 1 1. So this is a 1 0 1 1. I have to find the answer. So actually in the positions where a is containing 1, I will put 1 in my x at that positions. That will be actually my answer. That is the tricky part. Okay. Now, so not only that, here my actually what's happening is, here are 3 number of set bits, and in my answer in my a is actually also have a 3 number of set bits. Okay. Now what if there is a 4 number of set bits? There is 4 number of set bits. Now what will happen? So suppose a is 1 0 1 1 and b is 1 1 1 1. So the number of set bits of b is 4. So I need a x containing 4 set bits, right? So number of set bits of x should be 4. Now what can I say? Yeah, so let's take this number a 1 0 1 1. So definitely if the number was like 1 1 1, so if the number b has the same number of bits as my a, just a will be the answer actually in that case. Because if a is my answer, then actually after XORing a with x, I will just get this, which always be 0. Because in the places of where 1 is actually occurring, I have 1s in that places in my x, right? In the places where actually 1 is occurring in a, in the places where 1 is occurring in a, I have 1 in x. Here in this position, 0th position, 1 is occurring, here is a 1. In 1th position there is a 1 occurring, here is 1, and 2 there is no 1, 3 there is 1, so I have 1 here. Now I'm gonna put 1 here, because in that case this will be opposite signs, and here I will get a 1. So then our possible answer should be 0 0 0 0, and it becomes 0 1 0 0, right? So 1 1 1 1 is not a good option to choose. Now what if my number of set bits in B is greater than number of set bits in 1 A? So here is the number of set bits as 4, and I need a number x which has number of set bits as 4 also. Okay, so let's see. Now here, first thing is number of set bits of A is less than number of set bits of B, right? So first just put ones in the places of ones occurring in A. It is my A, this is my X. Just put 1 in the places where 1 is occurring in A. Just put them, okay? So I need some more ones, right? Because number of set bits in A is less than number of set bits in B. And I have computed my X as A initially. I am not done yet. Now I need some more X's. So where should I put the X's? I can put the 1 here, because it is like 0 0, right, up to 32 bit. The binary number is 32 bit, right? So this is 0th bit, 1th bit, up to 32 bit. After that all the rest part is 0. So we put 1 here, that is this, before this one there is a 1 here. What will be actually happen is these two bits will become opposite. So here I will get a 1, right? Now here is a 0 0 0 0. That's right, that's all right. But if I had a 0 in between, if I had a 0 in between the ones, then I have to put first 1 in there. Why? So here is my 1 0 1 1, and I'm doing the X right, like 1 1 0 1 1. So here is my 0, suppose. Okay, so it will give me answer 1 0 0 0 0. Now what happened if I put the 1 here? This is my X. My X was initially A. Okay, 0 1 0 1 1. I put 1 here. I put 1 here. Then it becomes this, and it's giving an answer this. Now I am putting 1. Here was my X. I am putting 1 here in place of this 0. Now what will happen is, here I will get a 0, here 0, here 0, here I will get a 1, but this one is actually giving me the minimum. Why? Because occurring 1 here is always be maximum than occurring 1 here, right? Because 1 0 0 0 0 is greater than 0 0 1 0, because this is what, 0 1 1 2 4 8 16. This is actually 16. This is 1 2. So I have to do the minimum thing, right? So I have to keep in touch with 0. As so far, so the more I get close to 0, the more I got the minimum number. Okay, so let me give examples. Okay, so example is the only thing to learn this binary tricks. So what I want to say is, first thing, that if a number of set bits in A and B are same, then A is actually my answer, because in the places of occurring 1 in A, I also have 1 in my X. So after doing the XOR, I will get all the bits as 0. So nothing can be smaller than 0, right? Because binary operation can give me a negative number in this case. And if I have the number of set bits of A is less than number of set bits of B, just first initially put X as A. Put my X as A. Now I need some more ones, because number of set bits of B is bigger. So I have to add some more ones to X to have the same number of set bits like B, right? So where should I put those ones? Suppose the case is like this, then I will start from searching from here. Where is 0? Here is a 0. Put 1 here. I will start searching from this right side in A. Where is my 0? I get a 0 here. So the first 0 I will get, I will put 1 there. Now my number of set bit becomes what? It becomes 4, right? Which is equal to 4. Then we are done. If our case is like this, 1 0 1 1 and 1 1 0 and 1 1 1 1 1. So here, suppose this is okay. So let's do this. Here is 1 0 1 1 1 and I have 0, and here I have 1 0 1 1 1. Oh, sorry. 1 1 1. So then number of set bits of B is 5 and number of set bits of A is 3, right? So here number of set bits of A is greater than number of set bits of B. So what I will do, initially just put X as A. So this is my A, this is my X, 1 0 1 1 0. Now there are what can I say, there is a lack of 2 ones, right? Because it has 3 ones, it has 5 ones. There is a lack of 2 ones. So I have to put 2 ones into my X. Put 2 ones in X. So where should I put it? I should put it in the beginning zeros, not in the ending zeros, because that will actually give, because I have put my X as A. So the place where I get a 0 will be 0 at, so I will have 0 in my A also, right? Because A is my X actually. I am putting X is A. So the place where I will get a 0 like this, I will have a 0 in my A also. So if I at the end side, that is the most left sides, I am just putting 1 there, I will get 0 here, 1 here. I will get a 1 here, which will give me a bigger number. So I cannot do that. I have to find the minimum number, right? So I will put the ones in the beginning parts. So here I will put 1. Now I will count in my A. So here I will put 1, right? So my now the yeah. So suppose I am doing the operations on A. You can do the operations on X, because I am initially putting X as A. I can do the operations on A also. So here is my 1. Now the current number of set bits is 4, right? So I need one more. So then I got a 0 here. So I will put 1 here. Now my number of ones is same as number of ones in B. So now I got the answer. So that is the case of when the number of set bits in A is less than number of set bits in B. Now what if number of set bits in A is greater than number of set bits in B? Okay. So I have 3 cases actually. The number of set bits in A is actually the number of set bits in B. Like the example 0 1 1 as my A and 1 0 1 as my B. So my X will be same as A actually, right? So my answer will be A. If number of set bits in A is less than number of set bits in B, first put X equal to A, then start searching from right. Where is my 0? In A. Place 1 in that places until I got my number of set bits of A is equal to number of set bits of B, right? And after that I will just put X equal to that A and return. Okay, like this 1 0 1 1 as my A and 1 1 1 1, then my B. So I will put initially x equal to 1 0 1 1. So this is my 1 0 1 1, putting x as also 1 0 1 1. Start searching in A. Where is my 0? Here is my 0, because there is a 4 1, here is a 3 1. So I need one more 1, right? So put 1 here and then place x equal to A. Okay, place x equal to A, or you can do that in the end part. Don't place x equal to A. Actually do this thing, do search 0 from right and place 1 until you get number of set bits of A equal to number of set bits of B. When both of them are equal, place actually x equal to A. Okay, that also will work. So that is the case. Now third case is number of set bits of A is greater than number of set bits of B. Okay, so in case of number of set bits of A is greater than number of set bits of B, then what we will do? Suppose A is 1 0 1 1 and B is 1 0 0 1. So think A is my initial answer. Now here is 3 set bits, here is 2 set bits, right? So I need to remove one set bit to become same as number of set bits as B. I have to become same as number of set bits as B, because my answer should have same number of bits as B. Okay. So I need to remove 1 1. I need to remove 1 1 from this 1 0 1 1. Now which should I remove? Now removing means that I am actually converting A to X. A is a separate case. A is A as there, but actually what I am doing is converting A to X. Then I will place x equal to A and return X. That's the thing I am doing. I am converting A to X. So which one should I remove? If I remove this one, it will become 0. Now 1 0 1 1, if I XOR it with 0 0 1 1, here is opposite number bits, right? So I will get a 1 here, right? I will get a 1 here. But what if I start doing it from the right side? If I remove from this side, I will get 1 0 1 0. After doing it with 1 0 1 1, I will get the opposite thing here in the first bit. So remember one thing, that opposite in last will make a number bigger than opposite in first. So first means the right sides, okay? So last means the left sides and first means the right side bits, okay? So here the opposite thing is happening. Here I will get a 1, all other 0. So which is bigger, 1 0 0 or 0 0 1? Obviously 1 0 0 is bigger. So to get a minimum number, I have to exactly do 0 in place where 1 is occurring. I will place 0 in place of 1. Then the number of set bits is actually 2, which is matching with B. So I will return x equal to A. Suppose A equal to 1 0 1 1 1 0 and B is equal to 1 1 0 0 0 0. So here is number of set bits as 4, here is 2. So here is my 1 0 1 1 1 0. Now I will use the contingency algorithm to find the first set bit here. I will place it by 0. I get another number. I will first find the first set bit. I find it here. I will place it by 0. Right? Then I have 2 number of set bits which is equal to this bit. So I will return the result 1 0 1 0 0. This will be my result. Why it's actually working is placing 0 here will actually give a bigger number, because then here was our original A, which was like this, okay, and here was our a which is converting to x. So this is suppose my answer x. So here both are opposite sign, it will give a 1 here. So that's why I am keeping the opposite signs at the beginning so that it can give a maximum number. So there are three cases, right? If number of set bits of A is equal to number of set bits of B, just put x equal to A. If number of set bits of A equal to number of set bits of B is greater than number of set bits of less than. If it is less than number of set bits of, I have to add some more ones. So where I will add? At the beginning zeros. I will add 1 and put x equal to A. If number of set bits of A is greater than number of set bits of B, I will remove ones from right sides. Okay, so if this is less than this, I will start adding or placing ones in the right sides, the first sides. Okay. First at the first position. And if I have this greater than this, I will place the one, I will remove the ones from right and place x equal to A. Now let's code. Okay, so I have three cases, right? Okay, so first of all I need to use the algorithm which will give me the number of set bits, or you can say count set bits, which will take an integer n. I will return that count. While my n is not equal to 0, I will compute the rightmost set bit, which is n and minus n, then do n equal to n minus rightmost set bit, then just to count plus plus, and I will return this count. That's very short part. Algorithm is very short, very little, but it's actually very magical. Okay. So now I'm computing the number of set bits for A. Okay. Count set bits, calling A. I'm just computing the number of set bits for A and B both. Okay. For B is actually count set bits B. Now there are three cases, right? If number of set bits for A is equal to number of set bits for B. Okay, so what I will do then? There are another case that number of set bits for A is less than number of set bits for B, or else the rest part, number of set bits of A is greater than number of set bits of B. So I'm creating an answer variable. I will place my answer, or you can say x, right? X, capital X. I will place just A, nothing else. Okay, and then I will return my answer. A, right? Sorry, X. If I have number of set bits of A less than number of set bits, so what will I do? I will start searching from right, and if I get a 0, I will do that. I will place that 1. Okay. So Yeah, number of set bits for A is less than number of set bits for B. Okay, so while number of set bits for A is not equal to number of set bits for B, I will do what? I will uh, do what is place 0, right? Yeah, so place 0. So let's do that by this. I equal to 0, I less than 32, I plus plus, and if I get my set bits, so I'm charging from right to left, right to left, the zeros. So if I get my bit as 0, so to check a bit is 0 or not, what I have to do? I have to do, I am checking A has 0 in that place or not. So I will do A and one left shift operator I, and that must be equal to 0. If that's the thing, then replace that by 1. See what I am doing. So number of set bits of A is less than number of set bits of B, right? So 1 0 1 1 and 1 1 1 1. So I was searching from 0 to 31st bit. So this is my 0th bit thing, which is 1. This is the 1th bit thing, which is 1. Here is my second 2th bit thing, which is 0. So we'll place here 0, right? So what I will do, I will create a mask. I will create a mask, okay, which will be like this. All zeros, here is a 1, other are zeros. So how to do this? This is my 2th bit, right? So I will place actually one left shift I. I is my 2. I is my positions that I am looping over. So what it does is actually, this is 31 zeros, then a 1. The 1 is actually what in binary? 31 zeros, then a 1, right? So if I is 2, it's like this. It actually shift this one to left twice. So first it shift this to here. Here is my 1. Then shift again. Here is my 1. So my number will like this 1 0 0. Okay, I have 0 0 1 0. Suppose if I left shift it by 1, it will become 0 1 0 0. If I do left shift again by 1, it will be 1 0 0 0. I have suppose 0 0 0 1. I left shift it by 2, it will become 0 1 0 0. Suppose this number I left shift 0 0 0 1, I left shift it by 3, suppose it will become 1 0 0 0. It will be like twang, then twang, then twang, 1 2 3. Okay, it will come up here. So I'm creating a mask like this, and I'm doing AND operation. So what will happen? All other zeros, right, in here. So after doing AND, all these will become 0. So if this bit is 0, I will get a 0 here, and all other are 0. So I will get actually a 0 if this bit is 0, and if this bit is 1, I will get a 1 here. So if my this answer is equal to 0, that means the bit here is 0. If this is not equal to 0, then the bit is 1. Okay. Suppose 0 1 0. So I am creating a 0 1 1. So I am creating a mask to check if this bit is on or off. So I will create a mask like 0 1 0. It will give me an AND operation and give me a result of 0 1 0, right? So this is 1. That means this bit is non-zero. Suppose this is 0. Then what will I get? 0 0 0, because all these are zeros, all these are zeros. So this 0 will give a result of 0 here, these zeros will give a result of zeros here, and this one depends on this bit. If this is 0, it will give 0, this is 1, it will give 1. In AND operation, 0 is powerful, very 0 is very powerful. If I do AND with 1, it will give 0. If I do AND with 0, it will give 0. And 1 is powerless, 1 will give as it is. Okay, this is the thing. So if my bit is 0, I will replace it by 1. So to replace 1, suppose I want to, I got a 0, suppose here is a 0, right? I want to replace this by 1. Now I found that here is a 0, that is, this condition is checking. I have to place also 1 here, right here. I am checking that here is a 0. Okay, I have to place 1 here, right? So I have to do that marks I have created. I will do XOR with it, XOR also. So I have to do OR, okay, OR with it. Suppose this is a number X, suppose, and this is a number Y. If I do X XOR Y, so 1 is very powerful in XOR. Okay, if you do XOR with 0, it will give you 0, sorry, so what I want to say is 1 is very powerful in OR operation. Okay, if you do OR with 0, it will make it 1. If you do OR with 1, it will make it also 1. 0 is powerless. If you do 0 with 1, it will give you 0. It will give you 1 as it is. If you do it with 0, it will give you as it is. Okay, so after doing OR with these two numbers, it will give me what? It will give me, so okay, suppose, so what I want to say is, so suppose this is the number 101, and I want to replace this by 1. So first find the marks, which is 0 1 0, then do OR. So all other here are 0, right? So this one will make it 1. So actually this bit will keep as it is, these bits will keep as it is, and as this is my 1, this mask is keep having 1 here, it will make this 0 as 1 here also. Okay, so that's how I am just making 1 here. See, 101 becomes 111. Okay, so this is the thing actually. This is a part of this small bit operation techniques. So we'll do A XOR 1 flip shift I. Okay, so I'll keep doing these things until I get, I have to give here a condition, until I get a number of set bits for A becomes, it was less than, right? So until it equals to the number of set bits of B, right? So if it is less than it, then keep doing these things. Okay, otherwise just stop. So this loop actually terminates. That means I get number of set bits for A is equal to number of set bits of B, because the opposite condition was given, right? So if this loop terminates, that means I get both of the number of set bits as same. So that means actually I got my answer. Just place X equal to A now. Okay, so yeah, so what was that part? What is that part is doing? What this part is doing? I have 1010 as A and B as 1111. So it has 4 set bits, it has 2 set bits. So I am just placing 1 in place of zeros. Here I place 1, I get number of set bit as 3, and here is also 4. So I have to keep looping over. Then I place this as 1. So now my both number of set bits becomes 10. I will just terminate. That's the thing is doing here. Okay, so now the rest part, right? That means number of set bits is greater than number of set bits for B. So I have to remove the ones. So where should I remove the ones? Where should I remove the ones? So number of set bits for A and is not equal to till my number of set bits for A is not equal to number of set bits for B. Keep doing this, and if it's done, that means number of set bits for A is equal to number of set bits for B. So just put x equal to A and we are done. Now what will I do? I will use the continuous algorithm, that is create a rightmost set bit which is A and minus A. Then I will do A equal to A minus that rightmost set bits. Now I get the first one, right? I got the first one. I will replace that by 0. So I will do A equal to A and replace that by, I will remove that, right? So I don't have to do that. I will do A equal to A minus rightmost set bit, that will remove the 1. I don't have to do anything. And simultaneously I will do number of set bits for A minus minus. So I am removing 1, right? So that's actually decreasing the number of set bits for A also. Okay. Now let's compile it. Okay, so in the case of where number of set bits for A is less than number of set bits for B, so I am actually placing what? 1 in place of zeros at the left sides, right? Yeah. So I have to increase the number of, set bits for A there. I should increase the number of set bits for A there, right? That's a simple thing. If I am placing 1, the number of set bits for A supposed to be increased. Okay, so we are done. So I hope you like the video, and if you understand the video and enjoyed it, then please do like, share and subscribe. Let's see you in the next video.